Hey guys, welcome back to day 32. We're talking about limiting reactant, theoretical, and percent yield today. So let's dive in right with an reaction. I have N2O, oxygen gas, going to NO2. All gases. So gas, gas, gas. If we balance the equation, 2 moles of N2O react with 3 moles of oxygen gas to produce 4 moles of nitrogen dioxide. So the mole ratio is a 2 to 3 to 4 is our mole ratio. The question says if, let's assume we have 3.0 moles of N2O, and if those 3 moles of N2O are mixed with 4 moles of oxygen gas, what is the maximum amount of product NO2 that can be produced? So right away we notice that 3 to 4 is a different ratio than 2 to 3. And so the reactants are not present in the correct mole ratio. One reactant will be either consumed or used up. Consumed is the more technical term, but used up, it's all gone first. So one reactant will be used up first, and we call that reactant the limiting reactant. And the limiting reactant always limits how much product can be produced. All other reactants are present in what we're going to call excess of requirements. We encounter this at home. You're making something. Doesn't matter what you're making. If you're making box brownies, you're making hamburgers, hot dogs, doesn't matter what we're cooking. There's usually some reactant that will be used up first. Chances are it's not your garlic powder if you're using garlic powder. Chances are it's not your ketchup. Chances are it's not your things that you buy in big volumes or big amounts to use in smaller pieces. But if you're doing blueberry muffins or brownies or a box cake, usually the cake mix, the brownie mix, the muffin mix, because it's one box, that a lot of times will be our limiting reactant. That limits how much we can make. In this case, how would we find which one's the limiting reactant? Well, I'm going to start with each. I have to use each. 3.0 moles of N2O. I'll have to perform my stoichiometry here. And we know that moles of N2O on the bottom, moles of product, NO2 on top, mole ratio, 2 N2O, 4 NO2. So it looks like we produce 6.0 moles of NO2 with our 3 moles of N2O. So with our 3 moles of our reactant, we can produce 6 moles of product because it's a 2 to 4 ratio. Makes sense. Oxygen, we're going to start with 4 moles of O2. stoichiometry with oxygen as well. We have 3 moles of O2 in our reaction and 4 moles of NO2, so that's going to produce about 5.3 moles, 16/3 of NO2. So which one is smaller? This one. So what does this mean? This means that O2 is the limiting reactant. A lot of times I will come up to a reaction and put LR and circle it. This also means that N2O is present in excess. I want to point something out. If you look, we have more moles of oxygen gas than we do N2O. The initial amounts does not mean you have, just because there's more doesn't necessarily mean that it's going to be in excess, and just because you have less doesn't mean it's going to be a limiting reactant. It depends on what you're using and what ratios. Another question that these problems will ask so we just determined the limiting reactant. In this case, 5.3 moles NO2 will be produced. It was a pretty straightforward problem because we started in moles. I gave you moles of our reactants. You had the balanced equation. Quick. What happens when we don't have the moles of our reactants right away? So a useful way to determine the limiting reactant is we divide the number of moles of each reactant by its coefficient in the equation. Of course, the lowest number is the limiting reactant. Why would we do this? Imagine if you have 3 reactants, not in moles. It actually makes it easier than it's quicker. It's quicker. Do you have to do it this way? Absolutely not. You can list every reactant out and go through to the end. Your call. I prefer this method. It's quicker, and we go there. So what do I mean by this? I have N2O, O2, and O2. Coefficients were 2, 3, and 4. We started with 3.0 moles of N2O and 4.0 moles of O2. What I like to do, and I'll do it in orange, I'll take 3 divided by 2. So the 3 comes from the 3 moles. The 2 is the coefficient, is 1.5. And I'll take 4 divided by 3, 1.33. Well, who's smaller? So all I do is circle this. Now, all calculations start with moles of limiting reactant, because that governs how much is required, how much is produced, everything. And then what I'll do is I'll draw a line through these. We don't want to use those. We just want to use the 4 moles. Another question that's commonly asked in these problems is how much of the non-limiting reactant remains at the end. The reason they ask you this is because they ask how much N2O remains at the end. Chances are oxygen's a limiting reactant. Now, it could not be, but that would fool or try to trick a lot of you. Not on purpose, but it's just that's how we would think. Oh, well, the other one must be the limiting reactant. Not the case. So it's asked how much of the non-limiting reactant remains. Well, in this case, what do you start with? We always start with the moles of limiting reactant. .0 moles O2. Moles O2 on the bottom, moles N2O on top. 3 moles O2, 2 moles N2O. If we do that, I get 8/3 or 2.7 moles of N2O consumed. Used, reacted. That's how much was used. Much was gone. So if we start with 3 moles of N2O and use 2.7 moles of N2O, that would show that 0.3 moles of N2O remain as excess. So you have to find out how much you use, how much reacts first. Then you go back to the start and subtract. That's how these are done. So that is limiting reactant right there. Let's do a problem of limiting reactant, and we'll come back to theoretical yield. So the problem is you have 6.54 grams of hydrochloric of zinc is treated with 5.47 grams of hydrochloric acid in solution. So you know it's aqueous. Here's the question. What is the maximum amount of H2 gas that can be produced? So we're looking for that. And 2 parts. It's kind of like take out the trash and put a new bag in the trash can. And what is the quantity of the non-limiting reactant remains at the end? So we have 2 parts to this equation. Is the equation balanced? Well, there is a 2 here, isn't there? Because there's a 2, you can assume that the reaction's balanced. 6.54 grams of zinc and 5.47 grams of HCl. Well, in this case, I have grams. I need to convert to moles. So step 1 will be convert to moles. And the question will be how many grams here? How many grams? That's the question. I can't really see that. There we go. Divide by the molar mass to convert to moles. Molar mass of zinc is 65.39. H is 1.01, chlorine is 35.45, so 36.46 grams per mole for HCl. For zinc, I get 0.100 moles of zinc. For HCl, I get 0.150 moles of HCl. Now we're going to figure out the limiting reactant. 0.1 divided by 1 is 0.1. 0.15 divided by 2 is about 0.05. 0.08, which means this is smaller. That's where we start, and HCl is my limiting reactant. So this is where we start. Start with moles of limiting reactant. So 0.150 moles HCl. Moles on the bottom. We're already in moles, so I don't have to do any more molar mass. Moles HCl on the bottom. Moles H2. And then we got to put down our coefficients. 2 moles HCl, 1 mole H2. And 1 mole of H2 is 2.02 grams H2. Now, in this problem, and I always talk about this in class, it just says amount. That could be moles or grams. I'm doing grams so that we do another step, just to be more example, but it doesn't say. So if it doesn't say, you can leave it in moles or you can take it to grams. It's your choice because it's moles and amount. So in this case, I get 0.152 grams H2 produced. And that's the answer to part 1, which was right there. Part 2 is now how much excess zinc. So for part 2, we're still going to start with moles of limiting reactant. 0.150 moles of HCl. Mole ratios next. We got moles of HCl, moles of zinc. Same coefficients. 2 for HCl, zinc is a 1. And then we're going to go to grams. Because it's easier to go to grams, because we have grams to start with. I guess we could go to moles too, it just doesn't say. But we're going to go to grams and do it in grams. We know that 1 mole of zinc is 65.39 grams of zinc. So that gives us 4.90 grams of zinc consumed or reacted. So we start with 6.54 grams of zinc. We use 4.90 grams. So that leaves us with 1.64 grams of zinc remains. One more example of limiting reactant here. Hydrazine reacts with dinitrogen tetroxide, and technically speaking, there should not be an A there, but I leave it there just because, again, I'm not going to grade you wrong if you don't drop the A. So hydrazine reacts with dinitrogen tetroxide according to the equation below. 2 N2H4 plus N2O4 going to 3 N2 and 4 waters. Now we have when 3 moles of hydrazine, which was this one, and 2 moles of N2O4, which is this one. The question is, how many moles of N2 are produced? Which is that one. Okay, I'm going to rewrite our equation. 2N2H4 plus N2O4 going to 3N2 plus 4H2O. We have 3.0 moles of hydrazine, and we have 2 moles of dinitrogen tetroxide. I need to find the limiting reactant. How do we do that? Well, divide by the coefficient. 3 divided by 2, 1.5. 2 divided by 1, 2, which means N2H4 looks like it's the limiting reactant. Draw lines through those. Start with the 3 moles. 3.0 moles of N2H4. And we got, it looks like 2 moles of N2H4 on the bottom. And we're looking for N2, 3 moles of N2 on top. So that will give us 9/5, 4.5 moles of N2 produced. Wonderful. Next topic will be percent yield. Now we know this. Sometimes the actual amount of product obtained in a reaction is less than expected. Sometimes the actual amount of product obtained in a reaction is less than expected. Think about baking cookies. For those of you who bake cookies, sometimes some of that cookie dough doesn't quite make it to the baking sheet, does it? Another thing that if you, no matter what you do, if you're making something, some type of food, whether it's on a grill, whether it's in a pan, a lot of times all the food that goes onto the grill or all the food that goes into the pan doesn't all come out. And how do we know that? Well, if it all came out, we wouldn't have to do dishes. That would be amazing for some of us. Some of us do dishes. Some of us don't. Some of us do. And those of us who do really would appreciate not having to do that. Just wiping the pan, rinse it, wipe it, you're done. That'd be awesome. People would buy those pans left and right. That's not how the world works, though. So dishes have to be done. But the principle that we're talking about here is that we know that not everything, every time we go from container to container, we're going to lose some in the transfer. We're good with that. You're saving your leftovers. You don't get it all out of the pan into the leftover container. We got that. Same thing happens in chemistry, in the lab. We're just not talking about something you eat usually. We're talking about a reaction we're doing. So this leads us to the percent yield. Which is the actual yield over the theoretical yield times by 100%. That's all it is. That's percent yield. The actual yield is measured. What was obtained in lab. The theoretical yield is calculated, right, on paper. What we got on paper. What we should get, in theory. I'm supposed to make 24 cookies. I'm supposed to get 24 cookies. The fact that we only got 18, I don't know what happened. Although we do know what happened. It's all good. It's all fun. This is no different than any other yields we've been talking about. Like if you got 95% on a test, you got 95 out of 100 questions right, or you got 19 out of 20 right. Same ratio. So it's just a ratio. Let's do an example. Uranium-6 oxide, which do not play with that at home, plus bromine trifluoride. Again, we're not playing with this at home. Don't do this. Goes to uranium-4 fluoride, bromine, and oxygen gas. The question is, what is the theoretical yield or theoretical mass of UF4 that can be expected? So, of course, it tells you to determine the limiting reactant and calculate the theoretical yield. You have to do step 1 to do step 2. So I'm going to rewrite my reaction. 6UO3 plus 8BrF3 going to 6UF4 plus 4Br2 plus 9O2. We're looking for how many grams here. We have 357 grams of UO3 and 357 grams of RF3. First thing we're going to do is divide by the molar mass. And if we divide by the molar mass, we can get moles. Well, what's the molar mass of UO3, uranium 6 oxide? Well, uranium is 238.03 plus oxygen 16, 3 of those. I get 286.03. Bromine happens to be 79.9. Fluorine is 19, and 3 of those. I end up with 136.90. Going to moles here, then I get 1.25 moles of UO3, and I get 2.61 moles of BrF3. Now we're dividing by the coefficient. So 1.25 divided by 6, I get 0.21. 2.61 divided by 8, I get 0.33. That means uranium 6 oxide is my limiting reactant, and we're going to start with this number right here, and I'm going to draw a line through those. We don't want to look at those. And now we're going to UF4. 1.25 moles of UO3. We know that it's 6 moles of UO3 to 6 moles of UF4. Pause. I recommend writing this out. Again, it's a communication skill and good for you for practice. Like, oh, it's a 1-to-1 ratio, just reduce it. I wouldn't do that. I would just leave it 6-to-6. You can see, you can just ignore it in your calculations, right? 6 divided by 6 is 1, so you can just ignore the pink. It's good to have it written out, though, so that, again, the whole point that we're getting to in science is that somebody can come behind you, know what you did, and do the next step. And so these little habits really do matter. Next, we're going to go to grams. We know that 1 mole of uranium 4 fluoride, do the molar mass, it's 314.03 grams of UF4. That gives us 392.54 grams, which ends up being 393 grams of UF4. And that's my theoretical yield. And why is it my theoretical yield? Because we calculated it. So we got 1 done. Limiting reactant, check. That was UO3. Theoretical yield, 393 grams. Number 3, suppose the actual yield is 380. So I end up with 380 grams. That's what we actually got. Less than the theoretical amount. What's the percent yield? Okay. Well, 380 grams, my percent yield. My actual was 380. In this case, it's from the problem. The theoretical is 393. And we calculated it. I'm going to multiply that by 100%. I end up with 96.7% yield. That's a pretty good yield. That's theoretical. yield, percent yield, actual yield, limiting reactant. Hope that works. Thanks for watching. We'll see you guys next time. Take care.